Hello, my dear students. So I'm back with the chemistry chapter called solution. We have started with the chapter, and we also have discussed many of the things regarding the chapter of solution. We'll continue now with respect to the concept we were discussing regarding the classification of binary solutions. Now we know what is meant by binary solution. It is nothing but mixture of two components, pure components, right? So we have discussed with definition part. Now, when we go for the classification of binary solutions, it can be classified into two main types or classes. One is referred to as a ideal solution, and second is referred to as a non-ideal solution. Now, what do you mean by an ideal solution and non-ideal solution? Dear students, please don't confuse with the concept of ideal gas and ideal solution. Ideal solution, we are studying here with respect to the concept of solution. We are studied ideal gas in the first year, right? Now, what is meant by an ideal solution? Ideal solution is defined as the solution which obeys Raoult's law. The solution which obeys Raoult's law at all concentration and temperature. Right now, we have discussed what in Raoult's law. Right. So, what is meant by Raoult's law? We have discussed already in the last video. You can just go through with that respect to the concept of Raoult's law. Now, so the definition of ideal solution is the solution which obeys Raoult's law at all concentration and temperature is said to be as what? Ideal solution. Now, similarly, opposite of that will be non-ideal solution. That is the solution which does not obey Raoult's law, right? So that is said to be as what? Non-ideal solution. So the solution which does not obey Raoult's law at all concentration and temperature is said to be as non-ideal solution. Now remember, children, ideal solution, if it is obeying Raoult's law, then the equation we know that Pa is equal to P naught A into mole fraction of component A. So if that equation is satisfied, then the solution is said to be an ideal solution. If Pa is not equal to P naught A into mole fraction of A, then if it does not obey the Raoult's law, then it is said to be as what? Non-ideal solution. Now for 1 marks, they may ask with respect to the definition of ideal solution as well as non-ideal solution. So I think you have understood with the concept of definition. So I repeat once again, ideal solution is nothing but the solution which obeys the Raoult's law at all concentration and temperature. Please students, do not write the answer only the solution which obeys Raoult's law. You should write the answer as what? The solution which obeys Raoult's law at all concentration and temperature is said to be an ideal solution. And similarly for non-ideal solution, don't write it does not obey Raoult's law. Please write the sentence completely. The solution which does not obey Raoult's law at all concentration and temperature is said to be a non-ideal solution. Now, here to explain the concept of ideal and non-ideal solution, you can see here. Here I have mixed the component A and B, right? So I here you can see blue balls and as well as red balls. Say for example, A is a solute and B is a solvent. So I mixed here. If it is obeying Raoult's law, the mixture of two components having same mole fraction, then it is said to be as ideal mixing. Now, if the force of interaction between the component A and B, say for example, here if I take red balls as a solute and I name it as component A, and blue balls as a solvent that is taken as blue color. Now, when I mix these two, right, so that is forming a solution of AB. Now, if the force of attraction between A and B are same, then it forms a ideal solution. Now, if the force of attraction between the A and B is weak, then it results into a negative deviation. That is, that results into a positive deviation where enthalpy delta H. We know that we are studied in what do you mean by delta H. That is change in enthalpy. Here, mixing MIX refers to mixing. So, change in enthalpy of mixing is greater than zero. If there is a strong force of attraction between the components A and B, then it results into negative deviation, right? So here enthalpy mixing will be lesser than zero, right? So this is a ideal solution. Now non-ideal solution are of two types. That is one is showing positive deviation, one is showing negative deviation. I will discuss with respect to types of non-ideal solution. Now remember, for positive deviation, enthalpy of mixing is always greater than zero. For negative deviation, enthalpy of mixing is always lesser than zero. Now I'll tell now individually with respect to the ideal solution what are its characteristics. right? So ideal solution, as I told here in the diagrammatic part, here red ball refers to solute and blue ball refers to solvent. So when the force of attraction between the solute and solvent are same, then it forms what? Ideal mixing. So here you can see the characteristics. The two liquids A and B forms an ideal solution when AA and BB molecular attraction will be same, and hence AB molecular attraction will be almost same as AA and BB. So, so the sentence is very simple one. So here you can see red balls are said to be A. The interaction between the red balls is said to be AA interaction, and the blue balls is said to be B. The interaction between the blue balls are said to be as BB interaction, or this we can say AA molecular interaction and BB molecular interaction. Now, say for example, red, as I said, it is solute, and blue ball represents solvent. If the force of attraction between, say I mix A and B together, now you can see here red and blue balls are together. That means I have mixed component A and B, that is solute and solvent. So if the force of attraction between the AB molecules is same as that of individual molecules, then it is said to be an ideal solution. So that is what the explanation here is. The force of attraction between A molecules, BB molecules will be same as that of AB molecules. So this is one of the important characteristics with respect to ideal solution. Now, the best example I can give you to explain this concept or this characteristics is, say for example, I have taken 10 ml of ethanol and I had as a component A, and in one more beaker I have taken 10 ml of water. Now you know that beaker A consists of 10 ml of ethanol and beaker B consists of 10 ml of water. Now I am going to mix ethanol in water. Now what should be the total ml? It is 10 plus 10, so total volume will be equal to what? It is 20. So here the force of attraction between AA BB will be same as that of AB molecular attraction. So for ideal solution, always the number of molecules or volumes remains same. It does not change or decrease. Now here, for also you can see here, for ideal solution, change in enthalpy or mixing of enthalpy will be equal to 0. Neither it increases, neither heat is evolved or absorbed during the mixing. Now apart from that, delta V, that is change in volume. So for volume also, as I had told, 10 ml of ethanol, 10 ml of water when I mix, both will be equal to 20. Neither there will be increase in the molecules or decrease in the volume. So hence delta V mixing also will be equal to 0. That is no expansion or contraction with respect to mixing. Now the ideal solution obey the Raoult's law. So what is Raoult's law? Pa is equal to P naught A into mole fraction of A. Pb is equal to P naught B into mole fraction of B. This is for component A and this is for component B. Now, which are the examples for this ideal solution? So you can say the examples for this one is ethyl chloride and ethyl bromide, and these are the two components. So N-hexane and N-heptane. Similarly, carbon tetrachloride and silicon tetrachloride. These are the examples for your ideal solutions. Now, we go for non-ideal solution. So I already discussed with respect to the definition of non-ideal solution. So what do you mean by non-ideal solution? The solution which does not obey Raoult's law at all concentration and temperature. Now, non-ideal solutions are of two types. First is said to be non-ideal solution with the positive deviation, and non-ideal solution with negative deviation. I think I discussed with the diagrammatic part in the previous slide, so I'll discuss in deep with respect to what is meant by positive and negative deviation. So trying to remember is non-ideal solutions are of two types. One is showing positive deviation and one more is showing negative deviation. Why does this positive deviation occur and why does this negative deviation occur? We'll study here one by one. Now, before I go for next one, so there is a note that for non-ideal solution, enthalpy, change in enthalpy mixing is not equal to 0, and change in volume is also not equal to 0. But for ideal solution, this is equal to 0. These are the two important points you should remember for non-ideal solution. Now, first type of non-ideal solution, that is a non-ideal solution with positive deviation. Now, what are the characteristics of non-ideal solution? Non-ideal solution showing positive deviation is, in such cases AB molecule interactions are weaker than individual molecules, that is A interaction or BB interaction. Now remember children, please, this is a little bit important one. In case of positive deviation, if I take the solution of AB, the solution of AB molecular interaction is weaker when I take the force of attraction between individual components, right? So I think this is clear. So you can see the diagrammatic part here. Now positive deviation you can see here. Here the concept is what? The interaction of AB will be weaker when compared to that of individual solute and solvent interaction. So that results in the formation of what? Positive deviation, right? Now and the absorbed vapor pressure of each component and the total vapor pressure are greater than the predicted Raoult's law. That means what? Whatever the vapor pressure is observed in individual components, that is A component and BB component, is always and the total vapor pressure are greater than the what is seen in the Raoult's law equation. Right? Now, for such a non-ideal solution with a positive deviation, PA is always, as I told, individual components force of attraction will be greater than that of your component solution. So PA will be greater than P naught A into mole fraction A component A, and similarly PB is greater than P naught B into mole fraction of B. Now children, you may ask what is PA, what is P naught A, and what is mole fraction of A. Similarly here, I had told again and again, I'm telling you, A and B are the two components. B is referred for solute and A is referred for solvent, say for example. Now, vapor pressure of component A is represented as PA, and vapor pressure of pure component, see here, don't confuse with respect to this and this is for vapor pressure of pure component A into mole fraction chi. This is the symbol chi, mole fraction of component A. So for non-ideal solution with positive deviation, partial pressure of each component A is greater with respect to vapor pressure of pure component, and similarly for vapor pressure of component B will also be greater than vapor pressure of pure component B into mole fraction of component B. Now if I see with respect to the total vapor pressure will be greater when compared to that of your vapor pressure of pure component A into mole fraction A and plus vapor pressure of pure component B into mole fraction B. So total vapor pressure will be greater. If it is greater, it represents what? Non-ideal solution with positive deviation. And vapor pressure of each component, if it is greater when with respect to the pure component, then it is also is for non-ideal solution for positive deviation. And as I had told earlier, the change in enthalpy will be greater than zero, and similarly change in volume will be greater than zero. So in one of the examination, they have asked one question regarding this in the board examination, that is, uh, if 10 ml of component A is mixed with 10 ml of component B, the observed solution is having the final volume 20.1, right? So what is the type of deviation? Now remember children, mixing will be greater than 0. Here you can see there is little bit, 10 plus 10 we should get 20, but it is the observation that they are given the value as there is due to contraction, and this one to contraction the volume total will be 20.1. So there is increase in the volume, so hence it will be equal to what? Positive deviation. And example for a non-ideal solution with positive deviation is cyclohexane with ethanol and ethanol in water, right? So these are two examples for positive deviation. Now, we'll go for the second type of non-ideal solution, that is with negative deviation. Now, for non-ideal solution with negative deviation, in this case, the intermolecular attraction of component AB is stronger than individual component AA or BB interaction. Now, don't confuse here. For positive deviation, this interaction is weaker, but for negative deviation, the solution interaction AB will be stronger than individual force of attraction between component AA or component BB, and observed vapor pressure of each component and total pressure will be lesser than. Now, in this previous slide, you can see Observed pressure and total pressure here is greater for positive deviation, but for negative deviation the observed pressure and total pressure is lesser than the predicted Raoult's law. So here you can see the same equation here. For negative deviation the observed pressure of component A is lesser, and similarly for component B it is lesser, and total pressure is also lesser. So these are the two points for indicating that pressure is lesser, so hence it is the showing negative deviation. And the change in enthalpy and change in volume is always lesser than zero. So I think 1 year or 2 years back they had asked in the examination, 10 ml of component A is mixed with 10 ml of component B, forming 19.9 ml of solution. What type of deviation it exhibits? Now, if you remember, the volume which we should get is equal to 20, but it is lesser than expected volume. So if it is lesser than the expected volume, then it is said to be for negative deviation, right? So these are some of the characteristics related to the non-ideal solution with negative deviation. Now, this is important part. We have explained with respect to the ideal solution, non-ideal solution. Under that, non-ideal solution can be classified into two types, that is showing positive deviation and negative deviation. Now, this is the graphical representation for the concept of ideal solution, non-ideal solution with positive deviation, and non-ideal solution with negative deviation. Now, say for example, this is the plot of graph of vapor pressure versus mole fraction. This is for component mole from component A, and similarly more component more fraction of component B. So when I plot a graph for component A, we'll get a straight line, right? Similarly for component B, we'll get a straight line. When I join these two, then I'll get the total pressure is equal to PA plus PB. So this is a graphical representation for PA and PB. This will be equal to total pressure is equal to PA plus PB. Now we know that the according to Raoult's law, for PB the equation is what? PB is equal to P naught B into mole fraction of B, and similarly for mole fraction A, that is PA is equal to P naught A into mole fraction of A. So when I join these two, right, the total pressure when I calculate, that will be equal to what? PA plus PB. Now this is for ideal solution. Similarly, here in this you can see the force of attraction between the individual components is same as that of your total individual component molecules. Now for positive deviation and negative deviation, you can see the vapor pressure for positive deviation will be higher when see with respect to the ideal solution. So I have explained already one example, that is if I take 10 ml of water and 10 ml of ethanol, if I get 20.1, so the volume is expected will be, vapor pressure will be greater than the ideal solution. So hence we get a graph where there is an extra line here. You can see this is the dotted line is indicating your ideal solution graphical representation, but for positive deviation you will get an extra increase in the vapor pressure surface. So hence there will be greater surface graphical representation when compared to that of your ideal solution for positive deviation. Remaining it is same, the graphical representation is same for vapor pressure versus mole fraction. Vapor pressure is taking towards the y-axis, mole fraction towards the x-axis. Now for negative deviation, the vapor pressure expected is lesser than that of your ideal solution. So the dotted lines here is for same as ideal solution, but the vapor pressure is lesser when compared to that of your normal ideal solution. So this is the representation for negative deviation. Now children, please do remember that the graphical representations are also asked in the examination for 1 marks or 2 marks depending. So hence these graphical representation, please practice and understand the concept, and it is very important. Now the main concept, or next we go for the important questions which will be asked in the examination, that is differences between ideal and non-ideal solutions, right? So very important one. Now, here you can see the differences between an ideal solution and non-ideal. So I had discussed already some of the points here. So one by one I'll discuss again. So it will be easy. Ideal solutions. So definition first will be the difference. It obeys the Raoult's law at all concentration and temperature. So the expression for Raoult's law is Pa is equal to P naught A into mole fraction of A. Pb is equal to P naught B into mole fraction of B. So hence it is said to be obeying Raoult's law. But for non-ideal solution, it does not obey the Raoult's law. So Pa is not equal to P naught A into mole fraction A, and Pb is also not equal to P naught B into mole fraction of B. Now, second difference between ideal solution is and non-ideal is, here there is a change in enthalpy that takes place during the formation of solution. That is, change in enthalpy is delta H mixing is equal to 0, but for non-ideal solution delta H mixing is not equal to 0. Similarly, change in volume is equal to 0, that is, there is change in volume during the formation of solution, whereas for non-ideal solution there is no change in the volume, that is delta V mixing is not equal to 0. Now, sometimes the definition that may be asked, that may be asked in the examination is between ideal solution and non-ideal solution. Sometimes they may ask the differences between ideal solution as well as non-ideal solution with positive or negative deviation. So for positive or negative deviations, so here you can see the differences here. For negative deviation, you can say Pa is lesser than P naught A into mole fraction of A, and delta H mixing is lesser than 0, delta V mixing is lesser than 0 for negative deviation. If they ask for ideal solution, this will be equal to 0. If it is for positive deviation, that means delta H mixing will be greater than 0 and delta V mixing will be also greater than 0. So based upon this, you can write the differences between the ideal solution and non-ideal solution. So for usually they will ask for 3 marks. The three simple definition you can write. This is important. So first difference is it states it obeys the Rolle's law. Non-ideal does not obey the Rolle's law. Here delta H mixing is equal to 0. It is not equal to 0 here, and change in volume is equal to 0. But here the change in volume is not equal to 0. So hence it is important, students. So hence remember the differences between ideal and non-ideal solution. Now we go for next important concept again, which is usually asked for 1 marks in the examination. That is called as azeotropic mixtures. Now the definition for azeotropic mixtures, it states that it is a constant boiling mixtures which boils at constant temperature. It is a constant. The boiling mixtures are having constant is said are constant which boils at constant temperature, and it distills over completely at same temperature without change in the composition. Now say for example I am taking components A and B, right? So they boil at the constant temperature and they come out as a same composition, right? Which there is no change in the composition, then those type of mixtures we say it as what? Azeotropic mixture. So the definition is very simple here. The definition is it is a constant boiling mixtures, right? So if I take AB mixture, right, it boils at a constant temperature and it will come out separately, right, without change in the composition. So those type of mixtures we call it as what? Azeotropic mixtures. Now there are formed by non-usual. This is very important one. These azeotropic mixtures are formed by non-ideal solutions. Right now, minimum boiling azeotropes are formed by those liquid pairs which show positive deviation from ideal behavior. Such azeotropes having boiling points lower than either the components. So this is a simple statement you can understand here. As a these type of minimum boiling azeotropes are formed. How does these azeotropes of having minimum boiling are formed? They are formed by liquid pairs which show positive deviation and also from ideal behavior or ideal solution. So such azeotropes having boiling points lower when compared to that of the components. So example for this one is C2H5OH, that is ethanol, and water. So the percentage composition you can see these distills out individually without changing in the composition, right? So this is for minimum boiling azeotropes. So for maximum boiling azeotropes, these are found by liquid which show negative deviation. This should be pair, liquid pair, PAIR. It should be which show negative deviation from ideal behavior. Such isotopes boiling point should be higher than the components. So example for this one is water with HCl, right? So the ratio is there given. So but mainly you can concentrate with respect to here the definition of azeotropic mixture. So it is a constant boiling mixtures which boils at a constant temperature and distills over completely without changing in the composition at same temperature. That will be called as what? Azeotropic mixtures. Now, dear students, we go for the main concept of this chapter, question number 28. Right, as I told in the previous discussion, will be one of the question related to colligative properties. Right, so 1 3 marks question for question number 28 will be there with respect to the concept of colligative properties. That is for 3 marks, and that too it is related to that of your numerical problems. We'll discuss what types of problems will be asked or what are the problems expectation we can do. Right, that all I'm going to discuss. after discussing the colligative properties. Now, here colligative properties. Colligate from Latin it refers to, so co means together, ligare means to bind. That means what? Together to bind. Now the definition of colligative properties is what? Colligative properties are those properties which depends only upon the number of solute particles present in a solution irrespective of their nature. So it does not depends upon the nature of the solution, it depends upon what? Number of solute particles present in the solution. So that property we say it as what? Colligative property. So how to define a colligative property? It is a property which depends upon the number of solute particles present in a solution irrespective of its nature. That we call it as what? Colligative property. Now, there are four types of colligative properties. First one is called as a relative lowering of vapor pressure. The first one is said to be as what? Relative lowering of vapor pressure. And the symbolic representation for relative lowering of vapor pressure is P naught minus P divided by P naught. So I repeat once again, the symbol for relative lowering of vapor pressure is P naught minus P whole divided by P naught, where P naught minus P is referred to as lowering of vapor pressure. I'll explain this concept when I go for the next thing, right? So relative lowering of vapor pressure is represented by P naught minus P whole divided by P naught. The second type of colligative property is elevation in boiling point, right? And it is represented by delta TB. B refers to boiling point. So the third type of colligative property is depression in freezing point. That is represented by delta T F. F refers to freezing point. So the last type of property is osmotic pressure, represented by the symbol pi. So there are four types of colligative properties called as relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, osmotic pressure. So now out of these four, any one will be asked for 28 question A for 3 marks. So each of the concept has got one numerical problems. So for one numerical problems carrying 3 marks, any one will be asked. So we are going to study one by one with respect to the concept. So first one will go for relative lowering of vapor pressure. Now, as I had told, relative lowering of pressure is represented by the symbol P naught minus P whole divided by P naught. Now remember, P naught is a vapor pressure of pure component, P is the vapor pressure of the component. Now, what is meant by relative lowering of vapor pressure? It is a ratio of lowering of vapor pressure to the vapor pressure of pure solvent. So, dear children, remember P naught minus P is referred to as what? Lowering in vapor pressure. So, to that ratio of vapor pressure of pure solvent, we call it as what? Relative lowering of vapor pressure. Now, the relative lowering of pressure of a solution containing a non-volatile solute is equal to its mole fraction of solute. That is, now this is the relative lowering of pressure P naught minus P divided by P naught. That is always equal to the mole fraction of a solute. So solute is represented by the symbol B, and A is representing solvent. So mole fraction of solute in the solution. So hence we can write the formula that P naught minus P divided by P naught is always equal to the mole fraction of the component B. B refers to here solute, right? So children, I am telling once again, don't confuse with the concept of relative lowering of pressure and lowering of pressure. Relative lowering of pressure is the ratio of lowering of pressure to the vapor pressure of pure solvent, whereas lowering of vapor pressure is a difference between vapor pressure of pure component to the vapor pressure, right? So P naught minus P is said to be as the lowering of vapor pressure. P naught minus P to the whole divided by P naught is said to be as what? Relative lowering of vapor pressure. Now this will be always equal to what? Mole fraction of the component B. B refers to a solute and A refers for solvent. Now we are going to derive one of the important formula related to that of relative lowering of pressure. How to calculate the molar mass of the solute, right? So we are going to derive, right? So in examination you don't have derivation, but the formula is very important one. So here P naught minus E is here P naught A minus P A whole divided by P naught A is equal to relative lowering of pressure of component A. Now this is also equal to NB whole divided by Na into Nb. We know that Nb what is number of moles of component B to the number of moles of component A plus number of moles of component B. So this formula I think we have already seen in the last class. So if you have any doubts, you can go for the concept clearance in the last class. You can see the video. Now for a dilute solution, now I can say dilute solution or ideal solution. Number of moles of component B is lesser than number of components of component A. So we neglect this B. Hence we take directly as what? Here see here, dear children. Number of moles of component B is lesser when compared to that of number of moles of component A. So hence we neglect this value and we take the value as only Na. Why? Because for ideal solution NB is always lesser than Na. So only Na will be kept here. So the formula becomes what? Nb divided by Na. Don't confuse where is Nb. Nb is nothing but for ideal solution this value is smaller. So hence we neglect this value. So hence when compared to that of Na value, so hence we neglect this value. So the equation becomes P naught A minus Pa divided by P naught A is equal to Nb whole divided by only Na. Right? Now simplify this. This will be same as here. Now this is what number of moles of component B. Now what is number of moles of component B? We know formula, right? Wb divided by Mb. So here you can see Wb divided by Mb, that is the weight of component B divided by molecular mass of B. Now number of moles of component A, so that is equal to Wa divided by this goes to Ma goes to the numerator. So the whole this expression Nb divided by Na turns into what? Wb into Ma whole divided by Mb into Wa. Now remember children, weight of component B, molecular mass of component A, molecular mass of component B, weight of component A. What is A and B here? A refers to solvent and B refers to solute. In some of the textbook they have given W1 and M1, W2 and M2. One refers to solvent and two refers to solute. Right? So here same. A refers to solvent and A refers to solvent and B refers to solute. One refers to solvent, two refers to solute. So when I simplify this equation, if I want to get Mb, that is molecular mass of solute. Mb is nothing but molecular mass of solute. So that will be equal to Wb divided by Wa into Ma into this equation. When it goes into numerator, this comes into numerator. Pa divided by P naught A minus Pa. So molecular mass of solute can be calculated by using formula weight of component B divided by weight of component A into molecular mass of component A into pressure of component A divided by vapor pressure of pure component A minus vapor pressure of component B, component A. So this formula is very important. Based upon this, we may get the problems for 3 marks. So here in some of the textbook they are given as M2. So if I take 1 and 2 as values, M2 is equal to W2 divided by W1 into M2 into Pa divided by P naught A minus Pa. So this is an important formula for calculating what? Molecular mass of solute, right? Now, or we can write the same formula like this. W2 to W1 as I told you. P naught A minus P naught 1 minus P1 whole divided by P naught 1 is equal to W2 into M1 whole divided by M2 into W1. So 2 refers to your solute, weight of solute, molecular mass of solute, molecular mass of solvent, uh, weight of solvent. Right. So either you can use this formula or you can use this formula, whichever you feel. This is simplified by directly we write as MB. So here you should simply calculate here M2. So simply for rearrange this one, you will get the same answer. Now, above expression is used to find the molecular weight of an unknown solute dissolved in a given solvent, as I told earlier, where Wb, weight of component B, and weight of component A, it is nothing but mass of solute and solvent respectively. So solute is Wb and solvent is Wa. And Mb and Ma are molecular weight of solute and solvent. Mb molecular weight of component B and molecular component of A. So here you can use B as either W2, M2, A and WA, or W1, MA, or M1. Right. So whichever you refer the textbook, based upon that you can, whichever you feel easy, that's the representation you can use. Now we'll go for the some of the problems related to that of rolling of vapor pressure. So this is the important one. So just concentrate here. can see here the first one problem is saying that 50 gram of sucrose whose molecular mass is 342, they have given the molecular mass in this, or is dissolved in 500 gram of water. The vapor pressure of pure water at 298 Kelvin is 23.8 millimeter mm. Calculate lowering of vapor pressure as well as relative lowering of vapor pressure of the solution. Now, dear children, this is very important problem, right? You can see here in the above question, 50 gram of sucrose. So this is your solute, that is a W2 or WB is given as 50 grams. M2 or MB, they are given as 342, dissolved in 500 gram of water. So 500 gram of water means what? So here this will be equal to what? W1, they are given as 500 of water. So whose vapor pressure of pure water means what? P naught A, right? That is equal to 23.8. Calculate lowering of a pressure as well as relative lowering. So to calculate that one, first you should know what is the number of moles of sucrose as well as number of moles of water. So I think in previous problems I have solved this equation. Number of moles is equal to given mass of solute divided by molecular mass. So given mass of sucrose is 50 gram, molecular mass of sucrose is 342 they have given. When I simplify this will be equal to 0.146 mole. Similarly, number of moles of water, that is N1, that is given mass is 500 gram, molecular mass of water is 18, that I simplify. When I simplify, I'll get it as 27.75 moles. Now, we know the formula relative lowering of pressure is equal to P naught minus P divided by T naught. So this always equal to what? N, that is equal to N2 divided by N2 plus N1. Now, how did you get this formula? Right? So we know that P naught minus P whole divided by P naught is equal to mole fraction of component B. Now, what is mole fraction? Number of moles of solute to total number of moles of solution, right? So this formula you should correlate here, right? So P naught minus P divided by P naught is equal to N2 divided by N2 plus N1. 2 refers to solute, 1 refers to solvent. So substitute here value. So this will be same, P naught minus P whole divided by P naught is equal to N2 value we know, that is 0.146, right? And N2 plus N1, simplify here, you will get the whole answer as what? 5.23 into 10 raised to minus 3. This is equal to what? P naught minus P whole divided by P naught. Now this is for relative lowering of pressure. Now I want to calculate, there is one more problem also, that is lowering of room pressure. So what is the formula for lowering of room pressure? P naught minus P is equal to P naught into N2 divided by N2 plus N1. Why it is like this? Because P naught minus P is lowering of pressure. So to get this one, this P naught will be multiplied here, right? So the equation you can, I think you understood, P naught minus P is equal to this P naught goes here, so P naught into N2 divided by N2 plus N1. Same here it is given. So substitute the value, we will get the answer as what? 0.125 m. We have calculated already N2 plus N1 value here. This value, that is 5.23. Substitute the value of P naught. They were already given in the equation. That is vapor pressure of pure water is 23.88. So substitute 23.88 into 5.23. Why 5.23? This value had come already with respect to N2 divided by N2 plus N1. So when I calculate, I'll get the lowering of vapor pressure as 0.125 mm. So I think this is clear with the first problem. In the first problem, we have calculated both relative lowering of vapor pressure and lowering of vapor pressure. Now similarly we'll go for second problem, that is the vapor pressure of water at 298 Kelvin is 23.75 millimeter mm. Calculate the vapor pressure over a 5% weight by weight solution of urea in water at the same temperature. Now they are not given much with respect to this, but by using this data we have to calculate the vapor pressure which is present over 5% weight by weight solution of urea in water at same temperature. Now how to solve this one, we will see. Now we know to calculate number of moles of solute, that is 5%, that is 5 divided by urea. Urea's molecular mass is 60. How it is 60? Formula of urea is NH2CO NH2. So substitute the values, you will get the answer as 60. So molecular mass of urea is 60. So N2, that is 5 divided by 60 is equal to this value. And they are given solvent as water. So how much? Now they are given 5%. That means what? In 100 ml, 5 ml is urea, 5 gram is urea, and remaining will be equal to water, that is 95 ml of water. So N1 is equal to 95 divided by 18. Why 18? The molecular mass of water is 18. So simplify this value, you will get as 5.278 moles. Now we know the formula, that is the relative lowering of a pressure is equal to N2 divided by N2 plus N1. So simplify these all values. So substitute, you will get the answer as a 0.3690. Right? So little bit it is not explained here, but the answer, whole answer is 0.3690. Now what is this? This is nothing but P naught minus P, lowering of your pressure. Lowering of your pressure is equal to 0.3690. Now I want the value of pressure, vapor pressure. So what is the formula? This P naught goes this side, P naught minus 0.3690. Now what is the value of P naught they are given? That is 23.75. So here in the problem you can see the vapor pressure of water is given as 23.75. So substitute that value here, minus 0.3690, you'll get the answer as what? 23.38 millimeter. This is what total pressure, right? So two problems, they are simple one. Just understand the concept and try to solve again and again, right? So I'll be giving some homeworks also later on when I go for the other completion of other concepts, right? Later on I'll give the homework, right? With these two problems, I think you understood the problems on relative lowering of work pressure. We'll go for last one, right? Type of problem on with respect to the vapor pressure, which is commonly asked in the annual examination, right? I will go with respect to the problem. So the third problem related to relative lowering of vapor pressure is, they are given the vapor pressure of pure benzene at a certain temperature is 640 millimeter of mercury. When 2.175 gram of non-volatile solute is added to 39 gram of benzene, the vapor pressure of solution was found to be 600 mm of Hg. Calculate the molecular mass of solute, assuming the solution to be ideal. Now, children, they are given much of the details here. You have to write the given things first. The vapor pressure of pure benzene, that means P naught value, right? So benzene here is your solvent, right? So solvent, uh, yes, it is a solvent. The P naught value for benzene is the given, that is a 640 mm of Hg. When 2.175 grams of solute, so they are given W2 value for solute is 2.175 gram, is added to 39 gram of benzene, so they are given W1 benzene weight, they are given as 39 grams, and the vapor pressure of solution, that is P value, it was found to be 600. So calculate the molecular mass of solute, that is either MB or M2, right? So how to solve this one? Now we know the formula, that is P naught minus P divided by P naught is equal to mole fraction of component B or 2. This is also equal to number of moles of component B divided by moles of number of moles of components of solution. So I think this formula we are studied during the concept explanation of mole fraction. Mole fraction is equal to the number of moles of solute to the total number of moles of solution. Now take this one, P naught minus P divided by P naught is equal to, now what is P naught value, they are given 640, P value they are given 600, P naught value is equal to 640, this is equal to N2 divided by N1, N2 divided by N1. Now where is this N2? They have given in the question that assume the solution to be ideal or dilute. So in the previous slide I had told, or explanation I had told, whenever the solution is ideal, the number of moles of solute is negligible when compared to that of number of moles of solvent. So hence here N2 value is lesser than N1, so hence we neglect this value, hence we take only the formula as what? N2 divided by N1. Now 640 minus 600 is equal to 40 divided by 640. Now N2 divided by N1. This formula we have seen. Number of moles of solute, W2 divided by M2. N1 is equal to W1 divided by M1. So I want the value of M2. So when I simplify this one, M2 will be equal to 640. This goes into the numerator into 2.175 into 78 whole divided by 39 into 40. So this is the rearrangement of these values, right? So when you rearrange this one, you will get the answer as 69.6. So that will be what? Now molecular mass of solute. So this is all with respect to the problem with respect to calculation of molecular mass of solute. So my dear students, so I think you have understood with respect to the concept of ideal solution, non-ideal solution, right? non-ideal solutions and a classification of non-ideal solution, right? So non-ideal solutions, and also we have seen the graphical representation for ideal solution, non-ideal solution with positive and negative deviation. Then we have seen the differences with respect to the ideal and non-ideal solution. Then we have gone for colligative properties. Before that, we also have discussed with azeotropic pictures. Then we have gone for colligative properties. So for 1 marks in the examination, they were asked how many, name any two colligative properties. So there are mainly four types. That is relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, osmotic pressure. So out of any four, you can write any two types of colligative properties. And we have started with the first type of colligative properties called as relative lowering of vapor pressure. And also we have solved the some of the problems related to that of your relative lowering of vapor pressure. So in the next class, I'll be discussing with respect to the other types of qualitative properties. So please, to children, if you have any doubts, please text me or please comments, do comments in groups or in the YouTube, and clarify your doubts. So hope if you have any doubts, please go through the previous slides also, which was explained with the concept. Which you, if you have missed any of the concepts, right? So hope you see this slide, and I think whatever the suggestions were given in the last slide, that notes were not clear, right? So based upon that, I have made some of the changes. So this is Suresh Bhatt from a chemistry lecture from working in Sri Sai Educational and Social Welfare Trust, Mudalagi, right? This is a Sri Sai's Science and Commerce College, that is Mudalagi. So if you have any doubts, please uh, text me, message me, or comment. Please do comments, and please go through the video carefully and understand it, right? Okay, so thank you very much.